This video is about making statistical inference involving two or more means, also known as the analysis of variance, commonly known as ANOVA. Recall that in making statistical inference involving two means, we may be working with two independent means wherein we're trying to compare two groups which are measured once. Or we may be working with two dependent means, meaning there is a single group measured twice, also known as the repeated measures, or when there is a matched pairs design. And if we have two independent means, we are using the student's t-test if we assume that the two population variances are equal. And we use the Welch t-test if there's an evidence that the two population variances are unequal, or maybe based on the f-test for two variances. And on the other hand, if we have two dependent means, we simply use the paired t-test. Now, in working with two or more means in case of independent means, meaning there are two or more groups measured once, and if we assume that the population variances are equal, we're going to make use of the Fisher's classic one-way analysis of variance, or simply known as the one-way ANOVA, or the single-factor ANOVA. And when working with independent means with two or more groups, and the population variances are evidently unequal, we're going to make use of the Welch analysis of variance, or the Welch ANOVA. Then, instead of the f-test for two variances, as the name implies is only for two variances, this time we're going to make use of the Bartlett's test. Bartlett's test is used to determine whether the population variances of two or more groups are equal or not. And further, when working with two or more dependent means, we're going to make use of the repeated measures analysis of variance. In medical researches, we use the Fisher's classic one-way analysis of variance in randomized controlled trials with two or more groups. Let's say there's a negative control group in which this group of patients are given a placebo or no treatment at all. A positive control group in which this group of patients are given the standard drug. And the treatment group in which these patients are given the drug which is to be tested. Or possibly three or more groups in which one group is the negative control while the rest are different treatments. Let's say treatment 1, treatment 2, and treatment 3. Further, repeated measures analysis of variance may be used in self-controlled trials when there's at least two measurements. So let's say there are three measurements in which the first measurement is the baseline, the second measurement is 6 months after, and another 6 months after is the third measurement. Now, let's proceed to the Fisher's classic one-way analysis of variance, which is a very common statistical technique as you read published research articles. Again, the Fisher's classic one-way analysis of variance is used when you're comparing two or more independent means, assuming that the population variances are all equal. Now, the Fisher's classic one-way analysis of variance is a statistical technique that involves partitioning the variance into different components to determine if differences exist in the means of two or more groups.
A randomized controlled trial wanted to determine the effect of daily intake of different yogurts in the HbA1c of type 2 diabetes patients in a span of 12 weeks. Yogurt A, or the control, which contains no vitamin D. Yogurt B, which contains vitamin D2. And yogurt C, which contains vitamin D3, were taken twice a day daily for 12 weeks. Their HbA1c in percent were measured at the end of the study, and results are shown below. Assuming equal population variances, do the data provide sufficient evidence that the mean HbA1c differ of those who took yogurt without vitamin D, yogurt with vitamin D2, and yogurt with vitamin D3 after 12 weeks? Test at 5% level of significance.
Keep in mind that these are the HbA1c after 12 weeks of 5 participants who took the yogurt without vitamin D. These are the HbA1c of another 5 participants who took the yogurt with vitamin D2. And these are the HbA1c of another 5 participants who took the yogurt with vitamin D3. Note that these are the HbA1c 12 weeks after taking the yogurt. And given the sample means, we'd like to determine that if we apply it in the entire population, will the population means be equal or not? So our null hypothesis is that the mean HbA1c of all those who took the yogurt without vitamin D those who took yogurt with vitamin D2 and all those who took yogurt with vitamin D3 are all equal. And as for the alternative hypothesis, we shall not write it in this form. Because although the alternative hypothesis implies that the mean of group A is not equal to group C, but maybe that the mean of group A is equal to B. Or maybe that the mean of group A is not equal to B, but the mean of group B is equal to C. Or maybe that the mean of group B is not equal to C, but equal to A. Or maybe that the means of A, B, and C are not all equal. The thing is, all these possibilities contains at least one equal sign. Thus, when there is at least one pair of means which are not equal, that is already enough to reject the null hypothesis. So the proper way to write the alternative hypothesis is that there exists at least one pair of means which are not equal. In other words, the mean HbA1c of those who took yogurt without vitamin D, those who took yogurt with vitamin D2, and those who took yogurt with vitamin D3 differ. Now for the test statistic, we have to complete this table in which our goal is to compute for the test statistic F, which has something to do with the mean squares between groups and the mean squares residuals. And in order for us to compute for the mean squares between groups and mean squares residuals, we also have to compute for the other values of the table. Let's begin to fill out the table, and we're going to begin with the DF of the residuals. As you can see on the data, there are 5 participants who took the yogurt without vitamin D. And since that is just a single group in which the DF is n-1, and since there are 5 participants, so the DF of that group is 5 minus 1, which is 4. And similarly, on the other group, wherein those are the participants who took the yogurt with vitamin D2, since there are 5 participants and the DF is n-1, so the DF is also 5 minus 1, which is 4. And similarly, on the other group, wherein these are the 5 participants who took the yogurt with vitamin D3, so the DF is also 5 minus 1, which is 4. Then all we have to do is to add those 3 degrees of freedom. We have 4, 4, and 4, in which the sum is 12. So the DF of the residuals is 12. As for the sum of squares of the residuals, which is also known as the sum of squares of the error, since we know that the variance is computed using this formula, what you notice is that the numerator there, which is x minus x bar, is also what we call as the error. So the numerator for the variance is the sum of the squares of the error. And the denominator, as you can see, is n-1, which you must know by now is the DF. So in other words, the sample variance is just the sum of squares error divided by the degrees of freedom. So if you need the sum of squares error, all you have to do is to multiply the sample variance with the DF. So the sum of squares of the first group is 0.235 times 4, which is 0.94. And similarly, for the second group, we have 0.22 times 4, which is 0.88. And for the third group, we have 0.185 times 4, which is 0.74. And similarly, we just have to add those sum of squares, and that will be the sum of squares in the residuals row. So that's 0.94 plus 0.88 plus 0.74, which gives us 2.56. As for the row total, that refers to all the observations regardless of the groups. So since there are 5 participants in group 1, 5 participants in group 2, and 5 participants in group 3, all in all we have 15 participants. And since the degrees of freedom is n-1, so that's 15 minus 1, and that gives us a degrees of freedom for the total, which is 14. As for the sum of squares of the total, since we know that the sum of squares is the sample variance times the degrees of freedom, so we need to get the sample variance of the 15 observations. And by using R, we get 0.592381. We may also open the file HbA1c, and to get the variance, we just have to type var HbA1c $HbA1c. And still we get the same value, which is 0.592381. That is why on this part of the data, it is stated that the sample variance of the 15 observations is 0.592,38095. And applying that the sum of squares error of the total is simply the sample variance of the 15 observations times its degrees of freedom. So we just have to multiply 0.592,38095 multiplied to 14 and we get 8.29334. And as for the first row, which is groups, we just have to consider that groups plus residuals is equal to the total. So in other words, the sum of squares of the groups plus the sum of squares of the residuals is equal to the sum of squares of the total. So to find the sum of squares of the groups, since the sum of squares of the residuals is 2.56 and the sum of squares of the total is 8.29334, then the sum of squares of the groups is 5.73334. And as for its DF, since the DF of residuals is 12 and the DF of the total is 14, then we know that the DF of the groups is 2. And note here that the degrees of freedom for the groups is simply the number of groups minus 1. So since we have 3 groups here, so 3 minus 1, we have 2. Then eventually, we may proceed in getting the mean squares of the groups and the residuals. Now, since the sample variance is the sum of the squares error divided by the DF, in which you must know that any sum divided by some function of n is like getting the mean. So in other words, the sample variance is actually the mean squares error. So to get the mean squares of the group, we just have to divide the sum of squares of the group with its degrees of freedom. So that's 5.73334 divided by 2, and we get 2.8666667. And similarly, for the mean squares of the residual, we just have to divide the sum of squares of the residual, which is 2.56, divided by its degrees of freedom, which is 12, and we get 0.21333. So in this context, we just have to remember that the sample variance is also known as the mean squares. Thus, the mean squares of the groups, which is 2.8666667, is also known as the sample variance of the groups. And similarly, 0.2133333 is the sample variance of the residuals. Now to get the F statistic, you're already familiar that the F statistic is computed using this equation. And in the analysis of variance, the numerator here refers to the groups and the denominator refers to the residuals. In other words, S squared sub 1 and sigma squared sub 1 refers to the sample and population variances of the groups, and S squared sub 2 and sigma squared sub 2 are the sample and population variances of the residuals. The thing is, under the null hypothesis, sigma squared of the groups and sigma squared of the residuals are equal. Because when sigma squared of the groups is equal to the sigma squared of the residuals, then the population means are all equal. But on the contrary, when the sigma squared of the groups is greater than the sigma squared of the residuals, that tells us that the population means differ. Thus, under the null hypothesis, sigma squared of the groups and sigma squared of the residuals will just be cancelled out in the calculation of the F statistic. So F statistic will just be computed using the sample variance of the groups divided by the sample variance of the residuals. So that is 2.8666667 divided by 0.21333, which leads us to 13.4375. So if the test statistic is 13.4375, and since the alternative hypothesis, theoretically speaking, is the sigma squared of the groups is greater than the sigma squared of the residuals, then that tells us that we are always performing a one-tailed test to the right in performing the analysis of variance. So in getting the p-value of 13.4375, we just have to get the area to the right of F equals 13.4375. And in R, we may compute that using 1 minus PF, and then 13.4375, and then the 2 degrees of freedom, which are 2 and 12, which are the degrees of freedom of the numerator and the denominator respectively. So the p-value is 0.000865. Now, as for the critical value, we have to make use of a different table since in the analysis of variance, we are always performing a one-tailed test which is on the right tail of the F distribution. So we have a separate table this time for the critical values of the F test. And taking a look at DF1 which is 2 and DF2 which is 12, we're going to have a critical value which is 3.885. And we may also compute that in R using QF 0.95, 2, 12. Which we may illustrate, suppose this is the F distribution, the critical value which is F is equal to 3885, and as we know, the area to the extreme of the critical value will always be the level of significance. Thus, it sets this part as what we call the rejection area. Now, where is the 13.4375? Is it in the area of rejection? Yes, it is in the area of rejection. Thus, we can say that we're going to reject the null hypothesis and conclude that there is sufficient evidence, then state the alternative hypothesis that the mean HbA1c of those who took yogurt without vitamin D, yogurt with vitamin D2, and yogurt with vitamin D3 after 12 weeks differ. And again, as for the p-value, which is the area here, we just have to compute that using R using 1 minus PF and then 13.4375, 2, 12, which gives us a p-value that is less than 0.001. Now, before we proceed with example number 2, let's just have a quick recap of how did we compute for the values in this table. We started with the DF, which is simply the number of samples per group minus 1. So since each group here has 5 samples, so 5 minus 1, we had 4. And getting the sum of that, we had 12. Next, we had to compute for the sum of squares, which is the sample variance times degrees of freedom. So multiplying this 2, we had 0.94. Multiply this 2, we had 0.88. Multiply this 2, we had 0.74. And adding these 3 values, we had 2.56. And next, we computed for the total, meaning we considered all these 15 values as a single set. So since we have here 15 samples, 15 minus 1 is 14. And the sample variance of these 15 values is 0.592. And with degrees of freedom and 14, so sample variance times the degrees of freedom, we had 8.293334. Then eventually, we computed for this sum of squares and DF of the groups. Since we know that the sum of this is this 1, sum of this 2 and 12 is 14. So we may get this value simply as 8.29 minus 2.56, we had 5.73. And 14 minus 12, we had 2. And eventually, we computed for the mean squares, which are just basically sum of squares divided by DF. So 5.73 divided by 2, we had this value. 2.56 divided by 12, we have this value. And eventually, we divide these two values, which leads to 13.4375. As for the next example, we're going to make use of the same example as in the previous topic, wherein this is about the number of visits of employees of those in the Medicare and the regular insurance program.
A study wanted to determine if the number of times employees visit a doctor per year differ according to the health insurance program, Medicare versus regular. Data are shown below. Assuming equal population variances, do this data provide sufficient evidence that the mean number of visits to a doctor of all employees with Medicare differ with the mean number of visits to a doctor of all employees with regular insurance program? Test at 5% level of significance.
Remember that we had our null hypothesis here in which the mean number of visits to a doctor of those in the Medicare and regular insurance program are equal. And our alternative hypothesis is that the mean number of visits to a doctor of those in the Medicare and regular insurance program differ. Now, what I want you to do here is to compute for the test statistic, but not by using the student's t-test. You're going to compute this time for the F statistic using the same procedures as of the previous example. So you may pause this video now and start calculating for the F statistic and resume playing once you're done.
A few minutes later.
Starting with the degrees of freedom here, 7 minus 1 we have 6, 6 minus 1 we have 5. And adding these 2 we have 11 as the degrees of freedom of the residuals. Next, as for the sum of squares, we have here 4.667 times 6 plus 1.90 times 5, whatever is that. The sum of those two values will give us 37.502. And 37.502 divided by 11 will give us a mean squares of 3.409273. And since we have 13 samples here, then the degrees of freedom, which is n minus 1, is 12. As for the sum of squares of the total, we have to compute for the sample variance of these 13 values, which when computed using R will give us 4.807692. Since sum of squares is the sample variance times df, thus our sum of squares for the total is 4.807692 times the degrees of freedom, which is 12. That gives us 57.6923. And again, since the sum of these two is equal to this, the sum of these two is equal to this, then we know that the sum of squares here is 57.6923 minus 37.502, which gives us 20.1903. And 12 minus 11 is of course 1. And note that this is 1, it's because we have two groups here, and 2 minus 1 is 1. And that gives us the mean squares, which is simply 20.1903 divided by 1, which is also 20.1903. And for the F statistic, we just have to divide these two variances, variance of the groups and variance of the residuals, which we have 5.922172. And for the p-value, we may compute using R using 1 minus pf of 5.922172, then the 2 degrees of freedom, which are 1 and 11, which gives us 0.0332. And given that F statistic, for the critical value, we may find that using the table by taking a look at the critical value when the DFs are 1 and 11. And that is 4.844. And we may also compute that using R using QF 0.95, then comma 1, comma 11. And so to illustrate that, this is the critical value F, 4.844. We know that this is 0.05, and this sets the area of rejection. And 5.922 is somewhere here, and thus we reject the null hypothesis and conclude that there is sufficient evidence that the mean number of visits to a doctor of all employees with Medicare is not equal to the mean number of visits to a doctor of all employees with regular insurance program. Then as for the p-value, we may compute that using R, using 1 minus pf of 5.922, 1, 11. And that gives us 0.0332. Consider here that I simplified the way on how to compute for the F statistic, because in most sources, you will see these equations on how to compute for the F statistic in the Fisher's classic one-way analysis of variance. And just so you know, the F distribution is named after Ronald A. Fisher. That's why it's F distribution, I guess, because F is Fisher and George Snedecor. That's why the F distribution is also known as the Snedecor's F distribution or the Fisher-Snedecor distribution. Anyway, in the analysis of variance, we have what we call as the post hoc analysis, which is performed only after when the analysis of variance rejects the null hypothesis. Because as we know, when the analysis of variance rejects the null hypothesis, it implies that the population means are not equal. So to determine where exactly those differences exist, we have to perform what we call as the post hoc analysis. In example number 1, we were able to conclude that there's sufficient evidence that the mean HbA1c of those who took 3 different yogurts are not equal. However, we were not able to determine which population mean is the lowest and the highest, since the analysis of variance just tells us whether the population means are equal or not. So to determine which population mean is the lowest and the highest, we have to perform the post hoc analysis. And we have many tests available for post hoc analysis. If we assume equal population variances, we may make use of the Tukey's honest significant difference, also known as the Tukey's HSD, which is the best of all pairwise tests in conserving the level of significance. Remember that multiple testing is not advised, since it increases the level of significance or the type 1 error. So what does Tukey's HSD do is that it conserves the level of significance. And we also have the least significant difference, which is the least conservative. We also have the Duncan's multiple range test, the Sheffie's test, and the Dunnett's test, which is only used when you're comparing multiple treatments to a single control. However, for this example, we're only going to make use of the Tukey's honest significant difference. If you are curious on what are the other differences of this post hoc analysis, I have posted in the description box below the link of the other readings. Now, going back in example number 1, again, our conclusion was that there is sufficient evidence that the mean HbA1c of those who took the 3 different yogurts differ after 12 weeks. So we have to determine which of the population means is the highest and or the lowest among the 3. So we have to perform the Tukey's honest significant difference. Now, to perform this, we simply have to apply the formula in which that is equal to Q and then the square root of the mean squares residuals divided by N. Now, for the mean squares residuals, we already have that in the table. N here refers to the number of samples per group, and the Q here may be computed using this formula in R. So if we're going to look for the value of Q, we simply have to make use of Q, Tukey, P equals 0.95, and then since we have 5 samples here for group, then we're going to make use of K as 5, and then the DF of the residuals as 12. So using Q Tukey, P equals 0.95, 5, 12, we're going to have a value which is 4.508. You may also make use of this Tukey's HSD table in which the row heading is the value of K, and 12 here is the DF of the residuals. So since our value of Q is 4.508, the value of MSR is already found to be 0.21333. The value of N is 5, since again we have 5 samples per group. So keep in mind here that Tukey's honest significant difference is only applicable when you have equal samples in each group. If in case the number of samples are different in each group, there's a modified formula for the Tukey's honest significant difference in that case. Now, substituting these values, we're going to have a value which is 0.931. Now, consider that this value of 0.931 is like your critical value, in which that will be compared to what we call a test statistic. Now, instead of a test statistic, we just simply have to compare this with what we call the mean difference, which we may found when we do what we call the pairwise comparison. Now, the pairwise comparison is simply a comparison of 2 groups at a time. So, meaning we're going to compare yogurt A with yogurt B, yogurt A with yogurt C, and eventually yogurt B with yogurt C. So we're going to compare the mean of yogurt A with the mean of yogurt B. Then we're going to compare the mean of yogurt A with yogurt C. And lastly, we're going to compare the mean of yogurt B and yogurt C. Now let's start with one pair. Let's say yogurt A versus yogurt B. We have a null hypothesis there that the mean HbA1c of those who took yogurt A and yogurt B are equal. And then the alternative hypothesis is that the mean HbA1c of those who took yogurt B is less than those who took yogurt A. The reason for this less than, it is because the sample mean of yogurt B, which is 8.2, is less than 8.4. So it is wise to hypothesize, given this sample means, that the population mean of those who took yogurt B is less than those who took yogurt A. So we just simply have to subtract 8.2 with 8.4. And we're going to have, let's say, negative 0.2. You may make use of 8.4 minus 8.2, so that gives you a positive value, which is 0.2. It doesn't matter. Now, all you have to do is to compare this with this HSD. So it is like you have a critical value of 0.931, positive or negative. It depends on the test statistic. So, since this is negative, you're going to compare it with the negative value of 0.931. So, since negative 0.2 does not exceed negative 0.931, so it is like you have a critical value which is negative 0.931. And negative 0.2 is just somewhere here. So, if this is your rejection area, then you're not going to reject the null hypothesis. So your conclusion here is that in favor of the null hypothesis, that the mean HbA1c of those who took yogurt B is equal to those who took yogurt A. Now let's have another pair. Suppose we have yogurt C versus yogurt A. Yogurt A and C. So we are comparing these two values. So our null hypothesis there, of course, is that the mean HbA1c of those who took yogurt A and C are equal. And then since, again, the sample mean of those who took yogurt C is less than those who took yogurt A, so it is wise to hypothesize that the population mean of those who took yogurt C is less than those who took yogurt A. So that's why this is less than. So 7.0 when subtracted to 8.4, or when 8.4 is subtracted to 7.0, that gives us 1.4 or negative 1.4. Now in this case, since this is negative, it's like having a negative 0.931 as your critical value, and negative 1.4 is somewhere here. And if this is your area of rejection, then we're going to reject the null hypothesis and conclude in favor of the alternative hypothesis, that the mean HbA1c of those who took yogurt C is less than those who took yogurt A. Now as for the last pair, we have yogurt B and yogurt C. So these two, we're going to compare 8.2 and 7. So null hypothesis is that the mean HbA1c of those who took yogurt B and C are equal. And the alternative hypothesis is that those who took yogurt B is greater than those who took yogurt C, since 8.2 is greater than 7. So subtracting those two, we're going to have 1.2 or negative 1.2. So it's like having positive 0.931 as your critical value, and your test statistic is 1.2. And since this is your rejection area, then we're going to reject the null hypothesis and conclude in favor of the alternative hypothesis, that the mean HbA1c of those who took yogurt B is greater than those who took yogurt C. Now later in R, how will you notice if you should make use of the less than or greater than in the alternative hypothesis? The key there lies in the sign of the mean difference. If this is negative, that implies that in the mean HbA1c of those who took yogurt C is subtracted with the mean HbA1c of those who took yogurt A is negative. So that indicates that this is greater than this one. So in other words, C is less than A, since again this is negative. So yogurt C is less than A, since again when these are subtracted, it leads to a negative value indicating that this is less than this one. So our alternative hypothesis here is that it is less than. Now as for the participants of those who took yogurt B and C, when the sample mean of those who took yogurt B was subtracted with the sample mean of those who took yogurt C, it leads to a positive value, then that indicates that those who took yogurt B has greater sample mean as compared to those who took yogurt C. So our alternative hypothesis there is that B is greater than C. So it's like having, if you have x versus y, then the mean difference is positive. Your null hypothesis, of course, the mean of x is equal to the mean of y. And your alternative hypothesis is that the mean of x is greater than the mean of y. Again, since this is positive, that's why this is greater than. If suppose x versus z is negative, then the null hypothesis would still be equal, but the alternative hypothesis is that the mean of x is less than the mean of y. And suppose we have y versus z and this is positive, then again, the null hypothesis is that they are equal, and the alternative hypothesis is that it is greater than. It is because this is positive. Then again, you just have to take a look later at the p-value. Let's say this is 0.03, 0.07, and 0.01. Then if this is 0.03, then we're going to claim in favor of the alternative. Since this is greater than 0.05, we're going to claim in favor of the null. And then since this is less than 0.05, we're going to claim in favor of the alternative. So that's how you're going to interpret later using R. Going back, since these are three conclusions, how are we going to interpret this now? Since B is equal to A, I'll just write it as A equal to B. C is less than A. So I'm going to put C lower than A since this is less than. So C is lower than A. Next, B is greater than C. So I'm going to put B higher than C. So B here is above C. So this indicates that C is less than this 2 and this 2 are equal, meaning the mean HbA1c of those who took yogurt C is less than the mean HbA1c of those who took yogurt A, and the mean HbA1c of those who took yogurt A is just equal to the mean HbA1c of those who took yogurt B at the end of 12 weeks. So our conclusion here is that it was evident that the mean HbA1c of those who took yogurt with vitamin D3, that is yogurt C, is less than those who took yogurt without vitamin D, so that is yogurt A, and yogurt with vitamin D2, that is yogurt B, after 12 weeks. While the mean HbA1c of those who took yogurt without vitamin D, so that is yogurt A, and yogurt with vitamin D2, which is yogurt B, did not differ. So in other words, if the goal of this research is to decrease the HbA1c after 12 weeks, it shows that yogurt C is the best among these three treatments. So the recommendation here is that taking yogurt C will decrease the HbA1c of type 2 diabetes patients.
Now let's perform everything in R. Note that all the datasets here may be downloaded using the link in the description box below.
So you may open the file, which is hba1c.rdata, and as you open the file, you may type hba1c, in which you will see there two essential columns, which are yogurt and the hba1c, which are basically these values that we saw on the table. And then just in case you'd like to see the descriptive measures, you may make use of the aggregate function. So you may take a look at the mean of the three groups, the standard deviation of the three groups, the variance of the three groups, as well as their sample size. Now, before we proceed with the analysis of variance, let us just verify if the population variances may really be assumed to be equal. So we have to perform what we call here the Bartlett's test. Again, the Bartlett's test is used to determine if the population variances across different groups are equal or not. So we have a null hypothesis there that the population variances are all equal, and the alternative hypothesis is that the population variances of the three groups differ. Or in other words, not all population variances are equal. So we may do that using Bartlett.test, and then the two essential columns we have HbA1c, then tilde, and then yogurt. Then data equals HbA1c. And then doing that, we're going to have a result in which the p-value is greater than 0.05. So since the p-value is greater than 0.05, this shows that the variances differ 97.34 by chance. So we may not say that the population variances are not equal. Or in other words, we're not going to reject the null hypothesis and conclude that there is no sufficient evidence that not all population variances are equal. So we may assume that the population variances are equal. So if the population variances may be assumed to be equal, and since we have three groups here, then we must use the classic Fisher's ANOVA. So to perform the classic Fisher's one-way ANOVA, we just simply have to make use of the AOV function. So we just have to replace the Bartlett test function with AOV. So AOV stands for analysis of variance. So AOV and then still HbA1c, tilde, yogurt, then the data, in which we're going to have this result. However, as we can see, this result doesn't have the p-value. So we may not see whether we're going to reject or not the null hypothesis. So what we may do is to modify the R function. Instead of just using AOV, we have to use summary and then the same function AOV. Then put everything in parentheses. So it will give you the same result as the one that we computed a while ago. So notice here that the sum of squares of the group of yogurts is the same, 5.73. We have 2.56. We have 2 and 12 as the degrees of freedom, and mean squares of 2.87 and 0.213. And we have the same F statistic, which is 13.44, and a p-value that is less than 0.001. So we have the same result as the one that we manually computed a while ago. Now, for the post hoc analysis, all you have to do is to replace the summary with Tukey HSD. Note that this is in capital T and capital H, S, and D. And then the same function, AOV, then HbA1c, tilde yogurt, data equals HbA1c. And then we're going to have this result. So remember, a while ago, I taught you about how to determine whether the alternative hypothesis is less than or greater than, and that will be applied here. Now, the first pair here is about yogurt B and yogurt A. So the null hypothesis is, of course, the mean of those who took yogurt A and B are equal. And the alternative is that since this is negative, then the alternative hypothesis is that B is less than A. And since the p-value here, this is called as the adjusted p-value, is 0.777, which is greater than 0.05, then we're not going to reject the null hypothesis and conclude in favor of the null hypothesis, in which the mean HbA1c of those who took yogurt A and B are just equal. Now, as for yogurt A and C, as for pair number 2, the null hypothesis is, of course, that the mean HbA1c of those who took yogurt A and C are equal, and the alternative, again, since this is negative, then the alternative hypothesis is less than. And since the p-value here is less than 0.05, then we're going to reject the null hypothesis and conclude in favor of the alternative hypothesis. Thus, we can say that the mean HbA1c of those who took yogurt C is less than those who took yogurt A. And as for pair number 3, which is yogurt B and C, the null hypothesis is, of course, equal again. But the alternative hypothesis here, a while ago we made use of greater than, since I intentionally compare their yogurt B versus C, while in this case it's yogurt C versus yogurt B. That's why their difference is now negative. So the alternative hypothesis here is less than. And since the p-value again is less than 0.05, then we're going to claim in favor of the alternative hypothesis. So given those three conclusions, again, since A is equal to B, so I'll write it as on the same level. C is less than A, so I'll write C below A. C is less than B, so C is still below B. In other words, the mean HbA1c of those who took yogurt C is less than those who took yogurt A and B. And those who took yogurt A and B just have the same HbA1c after 12 weeks. So we have the same conclusion as the one that was presented a while ago. So to have a sample write-up, if in case this is your research, for example, we may write it as, it was evident that the mean HbA1c of those who took yogurt without vitamin D, yogurt with vitamin D2, and yogurt with vitamin D3 after 12 weeks differ. So this is the result actually of the Fisher's ANOVA. And then what follows here is basically the result of the Tukey's HSD, that the mean HbA1c of those who took yogurt with vitamin D3, meaning this is yogurt C, is less than those who took yogurt without vitamin D. So this is C versus A. And that is C versus A with p-value of 0.001. And yogurt with vitamin D2. So this is C versus B. So that is 0.004. While the mean HbA1c after 12 weeks. While the mean HbA1c of those who took yogurt without vitamin D, so this is yogurt A, and yogurt with vitamin D2, this is yogurt B, did not differ. So that is A versus B, in which the p-value is 0.777.
Now let's proceed to the other analysis of variance for independent means, which is the Welch analysis of variance. But we're not going to compute for this manually because, as you can see, the equation for the Welch analysis of variance is more sophisticated as compared to the Fisher's classic one-way analysis of variance. So instead, we're just going to make use of R to generate the F statistic using the Welch analysis of variance. Just note that the Welch analysis of variance is used when the population variances are evidently unequal, and of course, we have independent means. But before we start, since the Welch analysis of variance is not a built-in function in R, we have to install a package which is called as the one-way tests. So to do that, we have to type install.packages and in parentheses and quotation marks, one-way tests, followed by library and in parentheses, one-way tests. And as for the post hoc analysis and the Welch analysis of variance, we're going to make use of the Games-Howell test. And again, Games-Howell test is not a built-in function in R. So we have to open a file which is the post hoc tgh.txt. Highlight everything, copy-paste in R, and then press the Enter key. Now that everything is set, we may already proceed with example number 3.
Naphthalene is found in cigarette smoke, car exhaust, and smoke from forest fires. Large amount of exposure of it may damage or destroy some red blood cells. When naphthalene vapors are breathed in daily, cells in the lining of lungs are damaged. Some even develop tumors. A group of researchers wanted to compare the serum naphthalene of cigarette smokers of less than 10 sticks a day, light cigarette smokers, at least 10 sticks a day, heavy cigarette smokers, and vape users. Use 5% level of significance.
So we may open the sigvape.r data, and as you open, you may type sigvape, and you will see these two essential columns which are groups and naphthalene. You may also take a look at the mean, standard deviation, and sample size by using the aggregate function for the mean, standard deviation, and the sample size. Now, since this deals with 3 groups, we have the light cigarette smoker group, we have the heavy cigarette smoker group, and the vape users. So we have 3 independent groups here, or 3 independent means. So that leaves us with 2 options, whether we make use of the classic Fisher's ANOVA or the Welch ANOVA. And to determine whether we're going to make use of the classic Fisher's or the Welch ANOVA, we have to perform the Bartlett's test. But first, let's just construct the null hypothesis. The null hypothesis here is that the mean serum naphthalene of the 3 groups are equal. And the alternative hypothesis is that the mean serum naphthalene of the 3 groups differ. Or in other words, at least one pair of the means of the naphthalene are not equal. So to determine again whether we have to make use of the classic Fisher's ANOVA or the Welch ANOVA, we have to make use of the Bartlett's test, in which the null hypothesis there is that the variances of the three groups are all equal, and the alternative hypothesis is that the not all population variances are equal, or in other words, the population variances of the three groups differ. Now let's perform the Bartlett's test in R using Bartlett.test, and then the two essential columns, which are naphthalene and groups, using the data sigvape. And we're going to have this output in which the p-value, as we can see, is less than 0.05. So this is 4.3 times 10 raised to negative 6. So since that is less than 0.05, we're going to reject the null hypothesis and conclude that there's sufficient evidence that not all population variances are equal. Now, since the population variances differ, or not all of the population variances are equal, then that shows that we have to make use of the Welch ANOVA. Now, notice that it's very similar to our previous lesson about two means, wherein if the p-value is greater than 0.05, before we have to make use of the student's t-test. Now, we have to make use of the classic Fisher's ANOVA. And if it is less than 0.05, before we have to make use of the Welch t-test, now we have to make use of the Welch ANOVA. So doing the Welch ANOVA here, we just have to type Welch.test. And then the same format, naphthalene, tilde, groups, and then the data, which is sigvape. And we're going to have a p-value which is 0.007. And since that is less than 0.05, then we're going to reject the null hypothesis and conclude that the mean serum naphthalene of the three groups differ. Now, to determine which of the population means is the highest and or the lowest, we have to conduct again the post hoc analysis. And for unequal variances, we have to make use of the Games-Howell. So this is the reason why we have to copy-paste the post hoc TGH file. It is because this is for the post hoc of the Games-Howell test. Now, for the Games-Howell test to be performed in R, we just have to type posthoc.tgh and then sigvape $, and then the quantitative variable, which is naphthalene, and then followed by sigvape again, which is the data file, and then $, and then groups. And we're going to have this result. So similarly, this is a pairwise comparison wherein it compared the light cigarette smoker versus the heavy, light versus vape user, and heavy versus vape user. So let's start with the light versus heavy cigarette smoker. Of course, the null hypothesis there is that the mean naphthalene of those two groups of smokers are equal. And then for the alternative, since the mean of the light smokers is less than those of the heavy smokers, then the alternative hypothesis is that the mean naphthalene of the light smokers is less than the mean naphthalene of the heavy smokers. And then we just have to take a look at the p-value here, which is less than 0.05, so we have to reject the null hypothesis, in which that implies that the mean naphthalene of the light smokers is less than the heavy smokers. Now, for the second pair, in which that is the light smokers versus the vape users, so the null hypothesis is, of course, they are equal. And the alternative hypothesis is that the light smokers have higher naphthalene content in their serum as compared to vape users, since 60 is greater than 27. And since the p-value here is greater than 0.05, then we're not going to reject the null hypothesis. So our claim will be in favor of the null hypothesis. So the mean serum naphthalene of the light smoker is just equal to the mean serum naphthalene of the vape users. And for the last pair, we have the heavy cigarette smokers and the vape users. And of course, again, the null hypothesis is that their mean naphthalene are equal, and the alternative is that the mean naphthalene in the serum of heavy cigarette smokers is greater than the vape users, since 218 is greater than 27. And since the p-value here is less than 0.05, then we're just going to reject the null hypothesis and conclude that the mean serum naphthalene of the heavy smokers is greater than the vape users. So summarizing these three, since light is less than the heavy, so I may write light below heavy. And then light is equal to vape, so I may write light on the same level as vape. And then heavy is greater than vape. So in other words, heavy is higher than vape, so I may write heavy as higher than vape. So in other words, the mean serum naphthalene of the heavy cigarette smokers is greater than the mean serum naphthalene of the light cigarette smokers and the vape users. And that the serum naphthalene of the light and vape are just equal. So if this is your research, you may write it as, it was evident that the mean naphthalene of the cigarette smokers and vape users differ. So this is the result of the Welch ANOVA. And whatever follows are the result of the post hoc here. So specifically, it was evident that those who smoke at least 10 sticks daily have higher mean serum naphthalene compared to those who smoke less than 10 sticks daily. So this is the comparison of the heavy and light cigarette smokers. So light versus heavy is 0.041. And those who use vape. So this is the comparison of heavy cigarette smokers and vape users. So heavy versus vape users is 0.015. And then those who smokes less than 10 sticks daily and use vape did not differ. So this is the comparison of light cigarette smokers and vape users, which is 0.219.
Now let's proceed to analysis of variance for repeated measures. Note that this is used for dependent means, meaning you have a single group which are measured at least twice. And to illustrate, suppose that measurements are done thrice.
A group of researchers wanted to determine if there are changes in the serum's total protein in grams per liter when using the red tab blood serum collection tube stored at a fixed temperature. Total protein are measured at baseline after 2 hours and after 4 hours of storage. Results are shown below.
So notice here that the mean total protein, as we can see, decreased from 68.7 to 64.5 and 63. But of course, these are just based on sample. Our null hypothesis here is that the mean serum total protein are just equal when the entire population are collected. And then the alternative hypothesis is that the mean total protein at baseline after 2 hours and 4 hours differ. So in other words, the null hypothesis is that the time has no effect, meaning the total protein did not change from baseline after 2 hours and 4 hours. Whereas the alternative hypothesis, it simply states that the time has an effect in the total protein of the serum when stored at room temperature, at baseline, after 2 hours, and after 4 hours. So you may open the red top cover.r data, and as you type red top cover, as you notice, there are two essential columns again, which are time and total protein. You may take a look at the mean, standard deviation, and length again using the aggregate function. Just note here that the layout of the analysis of variance for repeated measures works in this format, not on this format. So if your data looks like this one, let's say you have 15 samples measured at baseline 2 hours and 4 hours, sample number 2 measured at baseline 2 hours and 4 hours, you have to modify the layout of the data in this manner. So meaning you have to put all the numerical values in one column. So that means that the baseline will be in one column together with the values observed after 2 hours and after 4 hours. And then the time will be another column. So notice that 1 is for the baseline, 2 means this is observed after 2 hours, and 4 this is observed after 4 hours. And lastly, you have the ID column. So this means that the first sample observed at baseline 2 hours and 4 hours will be the ID1, observed at baseline which is 67, observed at 2 hours which is 63, and observed after 4 hours which is 61.92. Then let's say you have ID number 8, at baseline it is 68, baseline that's 68, 2 hours is 64.7, that's ID number 8, and after 4 hours it's 62.93. So after the data has been arranged in this format, then you may already go with the analysis of variance for repeated measures. So to perform the ANOVA for repeated measures, we just have to type AOV again, which stands for the analysis of variance, together with the summary, and then the total protein, and then tilde, and then time. And then what's new here is what we call the error function for the ID, which will match the total protein and time according to the sample ID. Then of course the data, which is red top cover. So we have two essential columns after the tilde sign. We have time and ID. After that, the analysis of variance for repeated measures will show a p-value which is less than 0.05. So we're going to reject the null hypothesis, which implies that there is sufficient evidence that the mean total protein at baseline after 2 hours and after 4 hours of storage at room temperature differ.
Since the analysis of variance rejected the null hypothesis, we have to perform the post hoc analysis. And for analysis of variance for repeated measures, the appropriate post hoc analysis is what we call as the Holm's p-value adjustment. And this may be performed using the pairwise.t.test function.
So this is just a pairwise t-test. So 2 at a time will be compared. And then red top cover, which is the file name, $sign, and then the two essential columns, total protein and time. Then paired equals true. So this declares that you are working with repeated measures. And then taking a look at the result, so these are just the p-values. So baseline and 2 hours, this is the p-value. Baseline and 4 hours is compared, this is the p-value. 2 hours and 4 hours, this is the p-value. To do the pairwise comparison, let's have the first pair, which is baseline versus 2 hours. So the null hypothesis is, of course, the two population means are equal, and the alternative is that the baseline is greater than after 2 hours, since 68.7 is greater than 64.5. And baseline and 2 hours have a p-value which is less than 0.05. So we may write it as less than 0.001. And that rejects the null hypothesis, and thus we conclude in favor of the alternative hypothesis. So the mean total protein at baseline is greater than the mean total protein after 2 hours. Next, for pair number 2, let's have baseline versus 4 hours. So the null hypothesis, of course, that their population means are equal, and the alternative hypothesis is that the baseline is greater than after 4 hours, since 68.7 is greater than 62.96. And baseline and 4 hours have a p-value again of less than 0.05. So we're going to reject the null hypothesis and conclude in favor of the alternative hypothesis. So baseline is greater than 4 hours. And lastly, for 2 hours versus 4 hours, of course, the null hypothesis again that is that they are equal, and the alternative hypothesis is that 2 hours is greater than 4 hours, since 64.5 is greater than 62.96. And 2 hours and 4 hours have a p-value of 0.044, which rejects the null hypothesis and concludes that the mean total protein after 2 hours is greater than the mean total protein after 4 hours. So collecting those three conclusions, we have baseline is greater than 2 hours. So I'll write baseline higher than 2 hours. So baseline is higher than 2 hours. Next, baseline is greater than 4 hours. So I may write it somewhere here. So baseline is higher than 4 hours. But 2 hours is greater than 4 hours. So in other words, this actually shall be written here, since 2 hours is greater than 4 hours. So we can say here that the mean total protein after 4 hours is less than the mean total protein after 2 hours, and the mean total protein after 2 hours is less than the baseline. Which basically shows that the mean total protein continuously decreased from baseline. So from the baseline, it decreased after 2 hours, and then after 2 hours again, it decreased again. So we may write the sample write-up results as it was evident that the mean total protein at baseline after 2 hours and after 4 hours differ. So this is the result of the analysis of variance for repeated measures. And then the succeeding lines are for the post-hoc analysis, which is the Holm's p-value adjustment. So this shows that the mean total protein when using the red top blood serum collection tube stored at fixed temperature decreases after 2 hours and after 4 hours. So this is a comparison of baseline in 2 hours and baseline after 4 hours. And it was also evident that the mean total protein decreased after 2 to 4 hours. So this is the comparison of 2 hours and 4 hours.
Now, before we end this video about the analysis of variance, since the student's t-test, the Welch t-test, and the paired t-test are used to compare two means, while the Fisher's Classic One-Way ANOVA, the Welch ANOVA, and the ANOVA for repeated measures is used to compare two or more means, can we just use this analysis of variance in comparing two means? Let me show you the same examples of the previous topic, which is about the statistical inference involving two means, but this time we're going to make use of the analysis of variance. And let us see the results.
In the Medicare.R data, which assumes equal variances, so we have here the result of the Bartlett's test, in which indicates that the population variances may be assumed to be equal. When we use the student's t-test, we have this result. And when we use the classic Fisher's one-way ANOVA, we have this result. Take a look at the p-value, the t-statistic, together with the f-statistic, and the degrees of freedom, as well as the degrees of freedom presented by the classic Fisher's one-way ANOVA. So to summarize, we have this t-statistic with df of 11 and p-value of 0.0332. We also have f as 4.5923 with df of 1 and 11 and p-value of 0.0332. And moving on, let's have the dengue.R data, which assumes unequal variances because the p-value based on the Bartlett's test, which is less than 0.05, indicating that the null hypothesis that the variances are equal was rejected. In making use of the Welch t-test, we have this result, and in making use of the Welch ANOVA, we have this result. So take a look at the t-statistic, the df, and the p-value using the Welch t-test, as well as the test statistic f in the Welch ANOVA, the degrees of freedom, and the p-value here. So the t-statistic is 14.321, df is 28.259, and this p-value which is less than 0.001. And likewise, we have the f-statistic here. We have the df 1 and 28.259, and p-value which is still less than 0.001. And on the HIV CD4.R data, so these are the same data except that the layout are different. It's because when we use the paired t-test, the data have to be in this layout, and when we perform the ANOVA for repeated measures, the layout has to be in this form. These are the same values as we see here, and this one for the baseline, and for the monitoring, we have these values. Applying the paired t-test, we have this result, and the analysis of variance for repeated measures, we have this result. Now observe the test statistic, the df, and the p-value. For the paired t-test, we have this t-statistic, df is 8, p-value is 0.0003. And for the analysis of variance for repeated measures, we have this f statistic, we have this 2df, 1 and 8, and we have this p-value, which is also 0.0003. Now, summarizing those three sets of results, we have this table. One thing that you must have noticed here is that the df of the t-test and the df2 in the analysis of variance are always equal. So 11, 28.259, and 8 for the third example. The df1 of the ANOVA is always 1. Remember that when we are comparing two groups, the df1 is 1. And when we are comparing two means independent, that's also the same as two means minus 1, so we have 1. Which simply states that if you are comparing two means, the df1 in ANOVA is always 2 minus 1, so that is 1. Consider also that their p-values are always equal, which shows that whether you use the t-test or you use ANOVA, the result will always be the same, as long as their df1 is equal to 1, or in other words, you're comparing two means. So the result of the ANOVA and the t-test are always the same as long as you're comparing two means, indicated by the df1 here. Now, regarding t and f, they are not equal, but there's a relationship between t and f. We have 2.4 here, and f is 5.923. We have 14.321 here, and f of 205.1047. And t of 6.2175, and f of 38.66. What you must notice about t and f is that when you square the t, that is always equal to f whenever you're comparing two means. Which shows that as long as you're comparing two means, or in other words, as long as the df1 in ANOVA is equal to 1, and for as long as the degrees of freedom in the t-test and the second degrees of freedom in f are equal, you will always have t squared is equal to f. And as demonstrated on the previous table, their p-values are always the same as long as this relationship holds true. Thus, it shows that if you are performing ANOVA and you have a particular value of f, let's say 4.0, rest assured that the result of that when using the t-test, that's equal to positive or negative 2. It is because when this is squared, that is equal to the f statistic. So if the df here is, let's say, 5, the df1 here is 1, and the df2 is rest assured to be 5. And the p-value here, let's say 0.1019, rest assured that the p-value here is also the same as 0.1019. So this basically shows that the result of the t-test in comparing two means is exactly the same as the result of the analysis of variance. So if you perform the student's t-test, that is exactly the same as the result of the classic Fisher's ANOVA. If you perform the Welch t-test, that is exactly the same as the Welch ANOVA. And when you perform the paired t-test, that is exactly the same as the ANOVA for repeated measures.
Vice versa, since the analysis of variance compares two or more means, while the t-tests are used in comparing two means, can we just make use of the t-tests in comparing more than two means? Let's say we're going to compare two means at a time.
To illustrate what happens, suppose this is the sample from group 1. And then this is the sample for group 2, and this is the sample for group 3. When you use t-test in comparing group 1, let's say you performed x bar 1 and x bar sub 2. You performed a t-test here. So that gives us an alpha which is 0.05. And then you compared, let's say, group 2 and group 3. So there's another alpha here which is 0.05. And then you compared group 1 and group 3. So there's another alpha here which is 0.05. Now the tendency here is that when you keep on using t-tests, you are increasing alpha. So it's not anymore 0.05. It's some function of 0.05, but surely it's a higher value. So the error here, since alpha is the probability of error, the error is now accumulated. So it's not wise to make use of t-test pairwise. That's why there is the analysis of variance, which conserves the actual value of alpha, which is 0.05. And that is what we actually mean here, that the Tukey's honest significant difference conserves the alpha even though it compares two means at a time. Now what ANOVA does is that it actually does not compare two means at a time, but rather it takes a look the means all at a time first. So this is alpha point with alpha 0.05. So to answer this question, can we just compare two means at a time using t-tests? The answer is no. It is because, again, using two means at a time, when comparing more than two means, you are actually increasing the alpha error. So it is not wise to make use of t-test two means at a time.
Now this ends this topic about the statistical inference involving two or more means, also known as the analysis of variance. If you learned in this video, you may click like, you may also subscribe for more videos soon. Stay safe guys!